Lidar and NODAR Hammerhead are two technologies for measuring 3D data for autonomous vehicles and autonomous robots. Lidar measures distance using time of flight. It measures the time it takes a photon to hit a target and come back, which is generally a very reliable way of measuring distance, and hence Lidar has become very popular for larger autonomous robots where safety is important and sensing needs to be beyond 5 meters to provide enough time to make a decision. NODAR Hammerhead is an ultra-wide baseline stereo vision product that also can similarly see beyond 5 meters out to 1,000 meters, and it can also determine 3D information in high density around the robot. It measures distance based on angles or triangulation, which is a physical measurement and therefore has the reliability needed for larger and faster robots. In this video, I will talk about 7 different parameters that are important in considering Lidar versus NODAR Hammerhead for your particular system. These 7 topics are range, resolution, bad weather, dust, vibration, low light, and cost. Range is an important specification. It determines how far a sensor can get 3D points. And this ultimately determines how fast your robot can go, how much time you have to make a decision, and how safe your system is. So having a large range is advantageous. And for a LiDAR system, the range is limited by the signal. So how much light can I send out in the world with my laser without burning out people's eyes? And that turns out to be about 100 to 200 meters maximum range. A NODAR Hammerhead system, an ultra-wide baseline stereo vision system, is not limited by signal. Sunlight's everywhere. If we were to say, what is the signal limited range of NODAR Hammerhead? Well, it would be 50 kilometers, which is the visibility on a clear day. In fact, this is not the parameter that typically limits the range of a stereo vision system. The stereo vision system is limited by its ability to discern something far away. That is, what is the range uncertainty? At some point, at some range, everything looks equally far away. And that's called depth uncertainty. Now, the depth uncertainty for a narrow baseline system is limited to maybe 5-10 meters range. And this is why stereo systems haven't been considered for the 50, 100, 200 meter range applications. So by going from these narrow baseline systems to now these ultra wide baseline systems of 0.5 meter to 1 meter to even 5 meters, you can now see anywhere from 10 to 100 times farther. And so the key innovation that NODAR had was the ability to really do wide baseline in a production manner, that is, making the calibration software work even when the cameras were moving around, to take advantage of this very long baseline. So the depth uncertainty for a 5 centimeters stereo vision system might have a max range of roughly 5 meters. Increasing that to 0.5 meter, that increases it to 50 meters. Increasing that to 5 meters, increases that to 500 meters. So there's a very straightforward mapping of angular diversity to maximum range for a stereo vision system. And NODAR's Hammerhead calibration and stereo matching software allows now a practitioner, a robot practitioner, to take advantage of a wide baseline mounted camera system to get very long range, high quality 3D point clouds to 100 meters and beyond. Resolution is a very important specification. It determines how precisely you sample the world in angular space. And this is important for finding small objects far away. It's important for identifying things. How many points do you need across a human to say it's a human? It's a critical parameter that needs to be compared between LiDAR and NODAR Hammerhead. LiDAR systems, there's a whole bunch of scanning mechanisms, but if we take the most common, the spinner, typically you have 64 channels across 30 degrees, or approximately 0.5 degree sampling in the vertical space. Horizontal is a bit denser at 0.2 degrees, but in general, that's kind of the resolution you have. 0.2 degrees horizontal, 0.5 degrees vertical, and for many applications, that's enough. For NODAR Hammerhead, it's a camera-based system. It's ultra-wide stereo vision, and the 30-degree hardware development kit that we sell has 0.01 degree resolution in vertical and in horizontal, which means that the horizontal is 20 times denser and the vertical is 50 times denser than the average spinner. This is important for a lot of applications. So for example, highway driving, finding small objects far away. If I have a tire that's 20 centimeters large, if I had a spinner, the spacing between those laser beams is approximately 20 centimeters at 23-meter range. So 23-meter range, hit or miss, it's not enough time for a vehicle driving at highway speeds to avoid objects. And this is why camera-based systems are desirable for those particular applications, because then you can see things like tires at 200 meters and 300 meters and beyond, which gives obviously a larger safety margin. In the factory, there's also advantages to having more resolution. You don't need to just be on the highway. There are fine structures in logistics centers that are important, such as forklift tines. Forklift tines are only 50 centimeters wide. These are the things that grab things, and they're getting hit all the time. Like robots run into these all the time. People run into them all the time. Super dangerous. So you need to be able to resolve those to be able to avoid them. And having the extra resolution of a camera-based system is incredibly useful. In fact, you can easily see these things at, for example, 50-meter range with a stereo vision system, whereas with the LiDAR system, spinner, you may miss it at 6 meters, so not very far. And there's another way to look at resolution. Often LiDAR companies like to report number of points per second, and so these points are not necessarily evenly distributed, but they're distributed somewhere in space. And LiDAR systems have anywhere from a few hundred kilopoints per second to, on the higher end LiDARs, 5 million points per second. In comparison, NODAR Hammerhead reports 50 million points per second, or 10 times more than these fancier LiDARs. So it's similar to having 10 128 channel LiDARs operating simultaneously. And that is another way to look at resolution. Harsh weather. Who doesn't want their sensor working in harsh weather, whether it's raining, snowing, fog? What we did at NODAR is take NODAR Hammerhead and compare it against a LiDAR system in an automotive environmental test chamber and compared the two systems in rain and in fog. What we found was quite surprising. The NODAR Hammerhead system performed 2 to 3 times better than the LiDAR system in fog and rain conditions. I'll link the article here. There's a publication talking about those results in IEEE. The physics is not super surprising. LiDAR typically has trouble with backscattered light. You're sending light from where the receiver is, and in a monostatic configuration, you're susceptible to distributed scattering, whether it's fog or rain or dust. The nearby returns typically overwhelm a LiDAR system and cause a degradation in performance. In a stereo vision system like NODAR Hammerhead, the estimation of range is different. There's a physically different mechanism, and that mechanism involves looking over multiple pixels to find the distance to a particular object. And because we're not looking at one laser beam or one pixel to make an estimate, we have a higher chance of discerning the distance to an object when there's obscurations. Secondly, there's the ability now to make advanced algorithms to see subtle features that are degraded by contrast, which is what rain and fog typically do to images. And this advanced processing allows us to see beyond the human limit. So there was one case during the testing where our researchers were like, there's no way we're gonna see through this 50-meter visibility fog. And just to put this in context, 50-meter visibility fog means that you can't see past 50 meters, or it's at a level that most people will not drive on the highway. They'll typically turn off. When you hear the weather report, when you hear 0 visibility, that's anything under 100-meter visibility. Okay, that's the context. So basically had an image that looked like it was full of clouds, and the human eye couldn't see anything in the range. And in the range, there was basically a wall, a car, a couple of objects, concrete blocks. And then we ran it through the NODAR Hammerhead processing, and lo and behold, out of this image came distance to these various targets. Now, of course, there was some degradation in the imagery, but it was estimating things that the human eye couldn't even pick up. And it wasn't hallucinating. It was essentially very subtle features that were being matched between the left and the right image. And so stereo vision has gotten to the point that it is now beyond what typical humans can do. In summary, you can take a look at the IEEE article, which I'll paste in this video. Basically 2 to 3 times more penetration through fog and rain compared to LiDAR. Low light. Low light conditions are important for operating a robot in nighttime conditions or places where there might not be a ton of illumination. In general, this is why a lot of robot designers use LiDAR systems, because they have active illumination sources, i.e. lasers, and these systems are broadly deployed in those types of conditions. However, new stereo systems actually have superior low light performance. We've run the best automotive LiDARs, long-range LiDARs, versus NODAR Hammerhead in test track conditions and have found very surprising results. In fact, on a test track, we put a variety of targets to detect, both with a 1550 nanometer long-range LiDAR system and a 1.2 meter baseline NODAR Hammerhead system, and found that the Hammerhead system saw targets anywhere from 2 to 4 times farther away. For example, a black pelican box was detected at 160 meters with the NODAR Hammerhead system, but only at 50 meters with the LiDAR system. Now, there was illumination. It was just standard headlights, but still, it means that nighttime or low light performance for stereo vision is actually at a very high level because of the new algorithms that allow matching features in high SNR images. So now one can expect 2 to 4 times extra range of stereo systems over that of LiDAR in low light conditions. Seeing through dust is really important for autonomous vehicles that are off-road. It's important for helicopters landing in sand. It's important for tractors dragging tillage instruments. Dust is everywhere, and often you want your sensor to be able to see through it. So LiDAR has typically had a lot of trouble in dusty conditions and is generally not considered for these conditions because of the backscattering effect. The laser and the receiver occupy the same space, and having a dust cloud in front of that receiver, that initial flash blinds the detector to anything that's behind it. Whereas for stereo vision sensors like NODAR Hammerhead, there's none of that going on, right? There's a much more conducive geometry to estimating range. Namely, dust, light to medium dust, all it does is reduce the contrast. Solar illumination is pretty uniform over the entire range band, and so estimating range to the object behind the distributed scatterer just generally is more robust as long as your algorithm can deal with these contrast reductions, which that's what NODAR Hammerhead does. And so in testing head-to-head with a LiDAR system, we typically find 2 to 4 times better performance. That is, we're able to see through it 2 to 4 times more than a LiDAR system. In extreme cases of dust, there's also the option of switching out the visible wide baseline detectors with long-wave infrared or LWIR sensors to get even more penetration through dust conditions. And this is just by virtue of the long-wave infrared wavelength, but it is also something that is compatible with the way that we do stereo matching, and so we can also service those particular cameras. Vibration and shock is an important specification, especially for off-road vehicles, helicopters that land in dust, or a piece of instrument that is vibrating and shaking. This is a condition that many LiDARs can't handle shock and vibe. In fact, the mean time between failure of a lot of the mechanical LiDARs may be between 15,000 hours or 9 months continuous operation to maybe 1 year to maybe 3 years. So replacing your product every 5 times during the lifetime of a product is an issue, which is not an issue for cameras. It used to be a problem for stereo vision. So stereo vision was very vibration sensitive, very shock sensitive until now. It's because if you measure angles and your cameras are vibrating, your ability to do stereo vision is compromised. At NODAR, we've developed a very, very well-performing calibration algorithm that calibrates every single frame to deal with vibration on the field, to be able to get high quality 3D with cameras in these types of environments. It's actually something that we're being told by even experts in the field. Why do you need to calibrate every frame? And it's because we want our systems to work off-road. We want our systems to work on vibrating machinery. And this is important because most of the vibrations, especially on cars, for example, are between 200 and 300 hertz. It's beyond the sample rate of most cameras, whether they're 30 hertz or 60 hertz. So in this sub-Nyquist sampled environment where the other calibration algorithms might operate over 100 to 1,000 frames, There's no way to compensate for vibration specs of, for example, tractors in the field without frame-to-frame calibration, and it matters. We've actually published some of the first data of what these cameras actually look like frame by frame. And there is no other data that shows that, because it's beyond the resolution of accelerometers, it's beyond the capability of existing calibration algorithms. So please check out our developer website and you can see what the world looks like to a camera, frame by frame. And compensating that vibration frame by frame is what really makes us and sets us apart and gives us a 3D sensing capability that no one else can touch, be it Lidar or other stereo sensors. Cost, one of my favorite topics. The cost of Lidar versus NODAR Hammerhead. So first, Lidar. You hear a lot about cost in the news, and by and large for the 64 or 128 channel spinners, you're looking at a price per Lidar in 2025 of $3,000 to $10,000 per unit, even at those volumes of hundreds to thousands. So that's not the full story, because you need to ask, how long is my product going to exist? If I have a car, if I have a tractor, if I have an AMR, I'm looking at, say, 15 years. But the mean time between failure for a Lidar spinner might be 1 year, might be 3 years, depends on vibration and how much you're using it. And if I'm, say, on the optimistic end, replacing my Lidar every 3 years, then 5 changes increases my cost from $3 to $10K to $15,000 to $50,000 per unit. And that's not the labor, right? That's just the bill of materials. And that is extremely expensive. So this is why people like cameras. Cameras can last 15 years. Cameras have no moving parts, and cameras have very good mean time between failures. And so the cost of a stereo system is basically 2 cameras and the cost of the processing. So again, if I look at automotive pricing for cameras, I'm talking about $25 to $50 per camera times 2, plus the cost of the compute. And we've done a lot of work at NODAR to reduce the computational footprint to a very small footprint on embedded hardware. The total cost of ownership and total cost of the hardware plus software is very compelling when compared to Lidar systems.